Remember the open loop from the beginning of this story, the 26 years and the 1000. Now you see why that mismatch matters. The 26-year silence that broke on July 12th was a blink. The 1,000 years without a major release on the Garlock and the 1,000-year high stress the new model sees on the neighboring fault systems, those are the real numbers. The little quake wasn't the story, it was the alarm clock. So here's what you actually do with this information. You don't panic. Panic is a terrible preparation strategy. You get ready, keep a 3-day kit with water, food that won't spoil, a flashlight, and a first aid kit. Know which sturdy table or interior wall you duck under when the shaking starts. Agree with your family on an out-of-town contact everyone can text if the phone lines jam. Put a pair of shoes by the bed. Download an early warning app so your phone can do what millions of phones did at 3:38 on a July morning. Say heads up a few seconds before the ground says hello. Earthquakes are one of the few disasters that give you decades of warning, not in the form of a date, in the form of silence. The silence is the message. California has spent a century learning to read it. The scientists who mapped the Plato fault, measured the Garlock's quiet weight, and built the early warning network that buzzed a million phones, they're all counting. The ground is counting too. The only question left is whether the rest of us will be ready when the silence finally ends. Since the July 12th quake, the region has been doing what it always does, releasing small reminders that it's still alive. Aftershocks have continued, most far too small to notice. To a seismologist, though, even the small ones are paragraphs in a story. Every aftershock helps map which parts of the fault web actually moved, where the stress shifted, and whether the Plato's rupture changed the load on its bigger neighbors. The most closely watched target right now is the western end of the Garlock fault. Remember, this is the fault with the 1,000-year quiet streak and the measurable stress bump from 2019. The question researchers are asking, did the July 12th shake transfer any new load onto the Garlock, or did it relieve pressure in some small way? You don't get that answer overnight. You get it by watching GPS stations, satellite radar readings, and patterns of microseismic activity over months and years. The broader 2026 picture is also being re-examined. Worldwide, the late spring and early summer were notably restless. Cuba took a 6.1, Baja California saw a 6.0, Northern California's Redwood Valley area was hit by a 5.6, and on that same day, Venezuela endured a catastrophic pair of quakes that killed thousands. None of this has been shown to be causally connected, but sequences like this are exactly what researchers study after the fact, looking for statistical patterns that only become visible with enough hindsight. Even the solar flare that briefly took out radio signals across parts of the Middle East and India hours before the California event will receive academic attention. Not because most scientists expect a real link, but because unusual timing is exactly the kind of thing that deserves to be checked rather than dismissed out of hand. The honest summary is that it's almost certainly a coincidence, but almost certainly is not certainly. The bigger thing to watch is the next version of the stress model. The team behind the 1,000-year study will likely update it with the 2026 events, including the Plato rupture, the Ridgecrest aftermath, and anything that happens in the coming months. That updated model, once it goes through peer review and publication, will tell us whether July 12th nudged the system toward or away from the limits they described. In the meantime, the public data feeds run around the clock. You can pull up the USGS earthquake page any day and see the same numbers scientists see in near real time. The agencies that run these networks publish their findings openly, brief reporters after significant events, and issue advisories when something changes. There will be false alarms, quiet stretches, and moments like this one, when a modest quake forces a very old question back into the conversation. All of that happens beyond your control. But while the scientists watch the ground, there is a piece of this story that is completely, entirely yours, and it won't wait for a peer review. Strip every forecast out of the story, and you're left with something most people missed entirely, the parts of this that actually worked and that were proven in the moment the ground moved. Start with the early warning. At 3:38 in the morning, hundreds of thousands of phones across Southern California buzzed with an alert before the strongest shaking arrived. That wasn't luck. It was the payoff of a sensor network built to do exactly one thing: give people seconds, sometimes just a handful of seconds, to stop, drop, and brace. Those seconds are enough for trains to begin slowing, for elevators to halt at the nearest floor and open their doors, and for a person to move away from a bookshelf. A 4.2 didn't require most people to use that time, but the system proved it could deliver. That infrastructure is real, testable, and standing. Second, the seismic network correctly identified the fault. Within hours of the quake, the Southern California Seismic Network had ruled out the San Andreas, ruled out the Garlock, and pinned the event to the Plato fault. That kind of rapid identification isn't glamorous, but it's the foundation of everything else. You can't understand a hazard you can't name. 20 years ago, this kind of source identification took days. Now it takes minutes. Third, the 26-year silence is documented. That's not a guess. The instruments have been listening in this region long enough that a quiet period like that can be measured, confirmed, and labeled. When seismologists say a fault hasn't moved like this in over 2 decades, they're reading a continuous log of the Earth's pulse. That log is the quiet, unglamorous machinery behind every headline in this story. Fourth, there's the humbling lesson from 2014. A magnitude 6.0 earthquake in Napa Valley broke a fault that researchers had never formally mapped before it moved. It simply wasn't on the books. In one sense, that's a warning about humility. Our maps of the underground will never be complete. In another sense, it's proof of progress. The scientific response to that quake was fast enough that the fault was characterized, analyzed, and added to the catalog almost immediately. The same thing happened with the Plato fault after July 12th. None of these achievements can tell you whether the next large California earthquake comes next year or in 30 years. But they're the reason an event like this doesn't have to remain a mystery. It becomes data. And data, not fear, not rumor, is what eventually makes a place safer. The same data stream right now is quietly pointing at what happens next. The most important thing to understand about earthquake science is that nobody can predict the next big one. That is not a small caveat. That's the whole ballgame. The stress model in that study is serious work, but it's still a model, an interpretation of the past built from incomplete evidence, and an estimate of the present that depends on dozens of assumptions. Change the assumptions, and the picture shifts. That's why it's called a model, not a forecast. There are also specific reasons to be cautious about reading too much into the July 12th event. The quake happened on a small, poorly understood fault. But small faults pop all the time for local reasons. A 4.2 on the Plato does not tell us the San Andreas is ready to move. It tells us a 4.2 happened on the Plato. Connecting one modest roadside shake to a 1,000-year stress clock is a very large leap, and most seismologists won't make it in those terms. Even the 2019 Ridgecrest finding cuts both ways. Yes, instruments recorded increased stress on parts of the Garlock after that sequence. But that same pair of quakes may have relieved stress on other nearby structures. The net effect on the timing of future earthquakes is genuinely uncertain. It could push things along, or it could turn out to be irrelevant for decades. Then there's the global pattern, which attracted far more attention online than it deserved. In the weeks before the Frazier Park quake, a 6.1 hit near Cuba, a 6.0 struck in Baja California, a 5.6 rattled Northern California near Redwood Valley, and on the same day, Venezuela was devastated by a pair of earthquakes that killed thousands. It's tempting to read that as the planet getting louder. The statistical truth is messier. Earthquakes are always happening somewhere, and clusters like this occur randomly all the time. Most researchers are careful to say that distant quakes don't trigger each other in any simple way. The timing overlap is a coincidence until proven otherwise. Even the solar flare that knocked out radio signals over the Middle East and India hours before the California quake has no established connection to ground shaking. A few researchers have explored whether intense solar activity could influence the upper atmosphere and, through a long chain of physical effects, nudge geological systems. That's an early-stage hypothesis, and most scientists treat it with heavy skepticism. When two things happen close together in time, a flare and an earthquake, the timing alone proves nothing. The mechanism hasn't been demonstrated. None of this means the stress study is wrong. It means it's a claim, not a conclusion, and responsible discussion has to keep it in that lane. But it also means the strongest, most defensible parts of this story aren't the predictions, they're the measurements that already happened. Let's be precise about what that study found, because the difference between what it actually said and what people might tell you it said is the difference between science and speculation. The study, published just weeks before the Frazier Park quake, focused on the southern San Andreas and a neighboring system called the San Jacinto fault. Researchers built a computer model spanning roughly 1,000 years of earthquake history, using evidence dug from trenches, offset landforms, and the geological record, and then compared present-day stress levels to every other point in that millennium. Their finding, according to the paper, is stark. Stress along these fault systems right now sits at or above anything the past 10 centuries can show. Not the past decade, not the past century, a full 1,000 years. What makes the result so hard to ignore is a feature of the landscape called Cajon Pass. It's a narrow corridor where the San Andreas and San Jacinto systems run unusually close together. The researchers describe it as a kind of gate. If a rupture were to start on one fault and reach that gate under the right stress conditions, it could jump to the second fault and keep going. turning what might have been a large earthquake into a single combined event that neither fault could produce entirely on its own. That possibility changes how scientists think about worst-case scenarios for Southern California. One researcher involved in this line of work, a professor who directs a major earthquake research center in the state, has argued that releasing the level of stress this model identifies would realistically require something on the order of a magnitude 7 or larger somewhere along that system. To put that in human terms, a magnitude 7 earthquake on that corridor could affect close to 24 million people across greater Los Angeles and the Inland Empire. That isn't a far-off fiction. That's the current population map of Southern California. And the historical context doesn't soften the picture. The 1994 Northridge earthquake, considerably smaller than what these researchers describe, still caused billions of dollars in damage and remains one of the costliest disasters in American history. That was more than 30 years ago. Since then, the region has added millions of residents and built vast new networks of roads, pipelines, and buildings. The target has grown while the pressure has kept climbing. Now connect the dots. The stress study says the southern San Andreas and San Jacinto systems haven't been under this much load in 1,000 years. The Garlock has been loading for up to 1,000 years of its own. And the Plato fault, silent for 26 years, chose this particular slice of history to wake up. It's entirely fair to ask whether that timing means anything. It's also fair to admit that the question is deeply uncomfortable. To understand why that clock is wound so tight, take a drive to the point where the San Andreas and the Garlock meet high in the mountains north of Los Angeles. You won't see anything special at first, just hills, brush, and a lot of sky. But the ground beneath your feet is a collision scene. The Pacific Plate is dragging the southwestern side of California slowly northwest. At the same time, a large block of desert crust is being pushed roughly eastward along the Garlock. Those two motions meet in the wedge of ground around Frazier Park. And since rock can't just vanish, the stress has to go somewhere. Think of it like two moving walkways in an airport, side by side, running in opposite directions. If you tried to stand with one foot on each, you'd feel the pull immediately. Now imagine rock doing that for millions of years. The faults in between are the seams where the motion finally gives. But here's the crucial part. Faults don't glide smoothly. They lock. The two sides of a fault get stuck against each other, the plate motion continues anyway, and the rock on both sides deforms, absorbing energy like a spring being wound. At some point, the lock breaks. That's an earthquake. The longer the lock, the longer the wind-up, the more violent the release. That's why the Garlock is the name that keeps researchers up at night. It runs roughly 160 miles across the desert, and trench studies along its path show it has produced enormous quakes in the deep past, some strong enough to offset the ground by several feet in a single instant. Researchers estimate it is capable of something around magnitude 7.5, and it has been quiet for somewhere between 5 and 10 centuries. Not far from this sleeping giant is the southern stretch of the San Andreas, which carries its own uncomfortable history. In 1857, the Fort Tejon earthquake tore through this region at an estimated magnitude of around July 9th. Before that, in 1812, a pair of major quakes struck the same broad area within days of each other. Since 1857, though, that stretch of the San Andreas has stayed quiet, more than 150 years of accumulating load with no major release. The big events California has seen recently, including the 2019 Ridgecrest sequence, have mostly happened farther east, out in the desert. Some seismologists suspect activity in this part of the state drifts back and forth between east and west over periods of half a century or more. If that pattern holds, the eastern cluster could be the tail of one phase with attention slowly rotating back toward the west. Then there's 2019 itself. The Ridgecrest earthquakes, a 6.4 followed a day later by a 7.1, the strongest to hit California in more than 20 years, did something researchers had never measured before on the Garlock. They left parts of it measurably more stressed. Instruments recorded ground movement along sections of the fault that had been pinned in place for as long as modern monitoring had existed. Since then, that extra load has been sitting there, adding to centuries of quiet accumulation. So by the time July 12th arrived, the region was already on edge in a way the public didn't fully appreciate. And then, weeks before the 4.2 actually struck, a separate team of researchers published a stress study that made the whole situation feel suddenly, sharply more serious. Here's what makes this whole story so easy to misunderstand. The numbers feel small, and they absolutely are not. A magnitude 4.2 sounds like a distant cousin of a 7.0. It isn't. Each whole step on the magnitude scale doesn't mean the quake is a little bigger, it means roughly 32 times more energy released. So a 7.0 is not about 3 times stronger than a 4.2. It's closer to 16,000 times more energy. And a 7.5, so the kind of event researchers believe the Garlock could eventually produce, would be roughly 90,000 times more energetic than that humble July shake. The difference between a 4.2 and a 7.5 is not the difference between a pebble and a boulder. It's the difference between a cap gun popping in a parking lot and a freight train derailing through a ravine. The sound is different. The feeling is different. The aftermath is different in every way that matters, but energy is only half the issue. The other half is time, and time is where human intuition really fails. 26 years of silence on the Plato fault sounds long, and it is, by human standards. A child born the last time that fault moved is now old enough to have a career and a mortgage. That genuinely feels like a long time. Now try this. The Garlock fault has not produced a major rupture in somewhere between 500 and 1,000 years, based on the evidence researchers have dug from trenches along its length. Depending on which end of that estimate you trust, the last time this fault truly broke, Norse ships were still crossing the Atlantic, or Columbus had only recently bumped into the Bahamas. Written records of California didn't exist yet. Spanish missions hadn't been founded. The pressure sitting in the ground today has been accumulating over a span that dwarfs the entire history of the United States. Take those two timescales and put them next to each other. The 26-year silence broke on a Tuesday morning in a way everyone could feel. The 1,000-year silence is still holding. Every year that passes, it gets heavier. Faults don't forget pressure. The rock on either side keeps grinding, locking, building tension, like a clock spring being wound a little more each day. That's the part you can't see from the surface. You can drive over the Garlock on a paved road, cross it without a second thought, read the roadside sign, and never realize that beneath the asphalt, two sides of the fault have been slowly accumulating strain the whole time. The ground doesn't check your calendar. It runs on a clock that measures itself in centuries. Right now, that clock is very, very wound. The version that raced across social media was simple, scary, and seductive. The 4.2 hit the junction of two of California's most infamous faults. It's an easy headline to sell, because the epicenter really was close to that junction. But when the scientists who run the Southern California Seismic Network sat down with the data, they reached a different conclusion. The quake was not on the San Andreas, it was not on the Garlock, it was on a much smaller fault called Plato, tucked into the hills west of the interstate near Frazier Park. Here's the part that makes people stop. Most Californians have never even heard of the Plato Fault. It has no disaster movie named after it. It has no documentary series. It has, until now, had almost nothing to say for itself. Records indicate it had been silent for at least 26 years when it woke up at 3:38 in the morning. That silence, not the shaking, is the part researchers are still talking about. To understand why, you need a picture of what this region looks like underground. Have you ever dropped a heavy stone onto a frozen puddle? The impact doesn't make one clean crack. It makes a starburst, a main split, surrounded by a dozen delicate fractures threading out in every direction. That is Frazier Park. The San Andreas and the Garlock are the two big, obvious cracks, the ones everyone names. The Plato is a hairline in the web, a side street that rarely makes the map. And the reason a side street like this can rupture on its own is that the whole neighborhood is under constant squeeze. Geologists who work here describe this corner of the state as a knot, not a line. Faults split, bend, and cross each other like a tangle of string. Some strands are mapped, some are barely named, some are probably still hidden. What's certain is that the squeeze is relentless. The San Andreas system carries the Pacific Plate grinding northwest. The Garlock accommodates a block of desert crust moving east. Between them sits this wedge of rock, taking pressure from both sides at once, like two delivery trucks trying to back into the same loading bay at the same time. There's no exit. The load just accumulates in whatever fault lines happen to be standing in the way. Sometimes the giants take it, sometimes the side streets do. On July 12th, the side street gave. Now for the uncomfortable part. You don't need the two most famous faults in California to slip for the ground here to shake. A quiet fault living in the crossfire can move entirely on its own, simply because it's been forced to sit in a vise for decades. That's a rare reminder that this entire stretch of ground is more loaded than public conversation usually admits. And it raises the question that has professional seismologists waking up early. If the side street can break a 26-year silence this easily, what is the main highway holding back? Frazier Park is not a place you plan a vacation around. It's a small mountain community on Interstate 5, about 70 miles north of Los Angeles, where drivers mostly glance at the exit sign and keep going. There's a gas station, a modest grocery store, a whole lot of pine trees, and until recently, very little reason to wonder what was happening underground. On the morning of July 12th, the underground reminded everyone it was there. At 3:38 a.m., the ground about 8 miles below the town let go. The quake registered magnitude 4.2. Though initial readings bounced between 4.1 and 4.4 before settling, that kind of shifting is completely normal in the first minutes after a quake, as more sensors feed in more data. What wasn't normal was how far the shaking reached. Bakersfield felt it, Santa Clarita felt it, Palmdale felt it, parts of Los Angeles and Orange County felt it. There were even scattered reports from the San Diego area, close to 300 miles from where the ground actually moved. Nearly 800 people filed reports with the U.S. Geological Survey before sunrise. Imagine being one of them. You're asleep. Your bed hums. The window glass shivers for 3 seconds. Then everything goes quiet. Maybe your phone buzzed a moment earlier with an alert from California's early warning network, enough time to sit up and brace, though for a 4.2, most people just lay back down, confused, and check Twitter. A second, smaller quake tapped the same area a few hours later, almost like the first one saying hello, and the second one confirming it wasn't a prank. There were no injuries, no damage, nothing broken. The whole event should have disappeared from the conversation by lunchtime. But here's the context you need before you file this under Earth Shrugged. California sees thousands of earthquakes every year, most so small that only instruments buried in the ground ever notice them. In a typical year, only 15 to 20 reach magnitude 4.0 or higher, and only Alaska sees more overall. A 4.2 is, statistically, background noise. So why did this one matter? Because of where it happened. And the story about where it happened spread online within hours, that it had struck the exact meeting point of the San Andreas and Garlock faults, the most dangerous junction in the state. That story, it quickly became clear, was very wrong. Right now, in Southern California, seismologists are still rechecking a quiet fault that woke up on July 12th after 26 years of doing absolutely nothing, and the timing is making everyone uneasy. The earthquake that broke that silence was only a 4.2. It didn't hurt anyone. It didn't crack a window. But it happened inside a tangle of faults that a brand new stress model says is carrying more pressure than at any point in the past 1,000 years. Here's the number that should break your intuition. It's not the 4.2. It's not the 26 years, it's the 1,000. One modest shake on a fault almost nobody has heard of in a neighborhood that has been quietly loading up for centuries, and a week later, scientists still aren't sure what it means. To understand why, we need to go back to the morning it happened, and the small mountain town that almost missed the whole thing.